you want, we can start. So thank you a lot, Carlo, for coming and discussing with us. So whenever you want, you can start.
Okay, let me just make okay, so now I see, I don't see myself, I see you. Wonderful. So first of all, thank you. Thank you very much, because I mean, both for having organized this, but also for all of you for being here, because of course, for me, this is this is a dream situation. I mean, that's, I guess everybody who writes, whether in philosophy and physics or whatever, I mean, the dream is having a bunch of people, I enormously respect, commenting, criticizing, saying how they look at what they can do with how they would take kind of thing that I wrote. So it was like Christmas for me. So thank you very much. It was really wonderful. And in this spirit, I'm not really answering, because for me, I mean, I've taken pages and pages of notes of everything was said. I'm going to reflect some of this. And for me, it was most about learning. And in fact, I listened to trying to learn the way you view relational quantum mechanics, what you do and what you think about it. So what I'm going to do is to take the five actually talks you gave, and just make some very simple comments where I think I might just, you might be interested in what is my perspective about a few things, but it will not be a response in any sense. So first one was Andrea about the PRB theorem, and it's how it's related to relational quantum mechanics. I mean, first of all, I obviously agree completely with what I heard. I think it was very good, very clear. Some people reacted by saying, well, in a sense, this was had already been remarked in some form. But what I think that what I heard is it's a very specific understanding of which one is the implicit assumption that is behind the theorem, and in which sense it plays into the theorem, is necessary to get to the conclusion of the theorem. So that was extremely clarifying for me. And the general remark I want to make here is this. I think this is an interesting case of the debate between different interpretations, because in a sense, to my surprise, having spent time with different interpretations, they are all far more coherent than when I thought at the beginning, each of them. And at least this might seem surprising, but then to think, Feynman used to say that a surprising thing about nature is that it allows different ways. The same phenomena allows different way of thinking about them, which interesting Feynman did not put as a sort of underdetermination of the theory, in the sense that he then recommended, he said any good theoretical physicist should keep several in mind, because one of them is going to be useful, one of them is going to be better to go ahead. So the point seems to me not what is, to some extent, not only what is coherent or incoherent in different ways to viewing quantum mechanics, but which one is the one that that can take us ahead better. And the common attitude is not okay, we have various ways of viewing quantum mechanics, but the common attitude is to see what somehow to blame of being wrong or absurd about other interpretation of quantum mechanics. And I think the reason is that each one of them, all the ones I know, the main ones, require us to give up some assumption, beliefs, some a priori, which seems completely natural and clear to many people. So the misunderstanding between people thinking about quantum mechanics in different ways is not seeing which one are the implicit assumptions which are discarded by one or the other interpretation of quantum mechanics. Some are very obvious, but some are much more subtle. And so the cleanest way, I think, to get some clarity is precisely to see which one is the argument. You see, it's not so much making an argument against an interpretation, but or for an interpretation, but to see which one are the argument on which the argument are based, which are assumptions which the argument is based. So this analysis of what is exactly the implicit assumption between P or B for me was extremely clarifying, because of course it made clear what seems hard to digest in relational quantum mechanics. To the people that don't find it interesting, and the same argument works for others. So that's a comment I wanted to make about Andrea. For me, it was very instructive. The second presentation was by Pierre, and let me just shift here. Pierre talked about this paper about locality, and he made a much wider presentation, and pretty nice in general, about locality, much wider than what is in the paper. By the way, the paper, I'm one of the authors, but I don't deserve it. It's really Pierre's idea, who developed and sort of used me as a bouncing table, and then insisted for me having me as an author. The key point, the technical point, again, it's a clarity one, namely something that was not clear to me before, which is that Bell locality, or more precisely Bell local causality, depend on the ontology that you choose. And so I think Pierre argued this nicely. When we think about locality and non-locality in quantum mechanics, it's a fact that the Bell inequalities are violated in a laboratory. That's, in that sense, quantum mechanics is non-local. I mean, if that's what we mean, go to a lab, measure them, and find something contrary to the Bell inequalities, quantum mechanics is non-local. But if you want to say from that local causality is violated, or some precise definition of locality is violated, you have to say what you assume to be the beable, you have to fix an ontology, and that's I think is a very clarifying point that Pierre has added to the discussion, because he has taken precisely, in the paper is more precise than in the presentation, in Bell language, the beable, so to say, of RQM, of relational quantum mechanics, and shown in which sense you don't have a violation of local causality if you have a system dependence beable instead of beables just attached to system by themselves. And there were a number of questions, and I was impressed by the question by Ding Jia that said, but then what is the meaning of epistemic here? In which sense the wave function is epistemic in relation to quantum mechanics? And Pierre sort of answered in a way which was technically correct, but I think it perhaps missed the point of Jia. Reaction, which I think I share, because there is a misleading, some of the words come with meaning, and of course in the HS, the Haring-Becker terminology, you distinguish between an ontic interpretation of the wave function and whatever is not ontic in the way they define it is called epistemic. So in that sense, obviously, the wave function is interpreted epistemically in relation to quantum mechanics. Okay, but epistemic implies that we buy the ontology in terms of which the HS story is built, that lambda, the realism about the lambda they talk about, which somehow, as Andrea pointed out, it's not part of the ontology of RQM. So it's not, so the result is that the wave function is not epistemic, it in relational quantum mechanics in strict sense, because one doesn't talk about episteme, one doesn't talk about knowledge, but one doesn't talk about the state of knowledge of the subject who learns, which is what the word epistemic immediately brings about. In fact, the way I view the physical interpretation of the wave function is very simple. It's in terms of the what a physicist does if in a new theory has something to interpret. You just take a limit where you know what you're talking about, and you take the classical limit of the wave function, you get the Hamilton-Jacobi function. And nobody would say the Hamilton-Jacobi function has an epistemic interpretation. What does this mean? Nor anybody would say that the Hamilton-Jacobi function has a realistic interpretation, even less. I mean, if you do the Hamilton-Jacobi function of a particle in classical mechanics, the particle is a little dot somewhere, and the wave function is all over. So that's not the ontology, but it's not the state of the knowledge, just a tool for doing calculation, a way of computing if this and that. Or if you want, as Pierre was saying, it's just a mathematical way of accounting of coding previous interactions between a system and another system, and on the basis of that computing the probability distribution of possible quantum event or values of variables in the next time they interact. So of course it's about probability, as it was mentioned. So I wanted to just emphasize this fact that saying that a wave function has it's an epistemic interpretation of relational quantum mechanics is correct in one sense, but it can be rapidly misleading if taken if too much weight is given to the word epistemic. And so what is real in relational quantum mechanics, what is the ontology of relational quantum mechanics, is, and here I may shift to the last discussion or anticipate something about the last discussion. One way you may have to view relational quantum mechanics is to say that there are systems. Okay, you talk in terms of systems, and systems have properties, but these properties don't refer to the system alone, but refers to what happened when the system interact with another system. So they only make their own description of the way the system affect other system, the way only description of something that happens when there is an interaction, and not description of something that happened by the system itself. So what is the ontology is about the value of these variables at interactions, which of course presuppose that we're talking about systems, and the entire formalism that we use in quantum mechanics is based on the idea that you take the world, you break it in systems, and anyway you break it in system, this game works. Now let me come to Alexia. That was the most critical of the point of the presentations about relational quantum mechanics, and I don't want absolutely to enter in a discussion what is better. All the general presentation that Alexia gave, I agree with the way she presents things. So I tried what I might do in a couple of minutes is try to pinpoint the way I understand the connection between the assumed ontology of relational quantum mechanics, if I may. So yeah, here probably is the right language, and the one of the context language that Alexia was referring to. And in fact, in the chat there was a comment by Philippe that made it pretty sharp. It's completely right what Daniele commented, that says, wait a minute, to say that something is relative to a context is the same thing as saying that something is relative to, with respect to another system. A system defines a context in relational quantum mechanics. Yes, so in a sense it's exactly the same kind of relationalism. The difference in what Philippe and Alexia want to do is that they want to restrict the kind of systems that count as good context. So out of all possible systems, there are the true ones that are the ones that, and they have an idea of what they are. And they are such that once a property is realized with respect to one of these contexts, let's consider this as a system, you don't have interference anymore, okay? And that's what Alexia says when say, well, then is a fact is a fact. And from the perspective of relational quantum mechanics, this is a subclass of the facts of the world, of the values taking, variable taking values. And it's a subclass that is actually realized. It's called stable facts. There's a paper by Andrea Di Biagio and me that describes this in detail, which happens when there is decoherence. And since decoherence is always approximate, obviously, and in a sense is also system dependent, because decoherence is with respect to a system which ignores the environment. So Richard Healey was completely on the point, saying, well, if you have the coherence, then you have the context in your sense. Yes, exactly so. So we're talking about, what you're saying about is it's coherent on the relational side and on the contextual side. The split is only in the following in this. I mean, the fact with respect to a context are taken as fundamental, are called fundamental in the context case. So I want to call fact only something which has been measured by something large enough, microscopic enough, with sufficient number of degrees of freedom, so that forget about possible interference between this and other branches. Relational quantum mechanics is the attitude is say, well, let's call facts a much more wider set of things that don't require decoherence, don't require infinite large things. And among these facts, there are those which are stable, and we understand why they are stable because we understand decoherence somehow. This is sort of what Richard was saying also, and I want to just say, so it's clear, I think, the relation between the two perspectives, just in a sense, out of the same theory, given the same prediction, which one do we want to count as elements of reality, a larger or a smaller sect? And only one little comment Alexia made, sort of, I understand it's a sort of rhetorical move, but she was sort of politically connecting that. Well, if we say that facts are relative, you know, everything is true and fake news, and we go in the direction of total relationality, which is what we don't want. Yeah, of course, but then, you know, this is like saying, you know, when Einstein wrote relativity, people say, oh, no, we shouldn't go relativity because then, you know, the young people doesn't respect the old people anymore. I don't think, if nature forces us to some degree of relationalism, this doesn't mean that we have to fall into the fake news and the flat earth things. Stable facts are very stable. The earth is round and not flat, and so on and so forth, obviously. Good. So then the last talk, or the last two talks, sort of Mauro and Matteo, for me were extraordinarily instructive. Let me make this point. I'm definitely a physicist and not a philosopher, right? I'm in the way I think also. I am extremely interested in philosophy. I try to steal from philosophy, to get ideas from philosophy, to listen to philosophers, to be inspired by or to be liberated by philosophical thinking. But I think in physical terms, and so the point for me is not even so much rigor in thinking, which is a point for many of you, but is what is the best conceptual structure for understanding the world at the light of what we have learned so far. And that's also the way I view questions about ontology or questions about the interpretation of quantum mechanics. I mean, given the fact that we've learned about the world the fact that there are correlations between what we see, the fact that there are numbers, so and so. What is the organization of concepts, ideas, and facts that better works? So it's not really how is the world, but it's really how at best we can think about the world given what we have learned so far, where the conceptual part follows the knowledge part. I mean, given the pile of huge information we have to learn about the world, what's the best conceptual structure in terms of which to organize this? This was a preliminary point. The argument of Mauro about priority monism, or I should say against priority monism, is something that, you know, I first encountered his paper on that some time ago, and it took long for me to digest it all the way through. But I think I am 100% sympathetic to it, not as a philosopher, but as a physicist. One of the questions that are you arguing for logical impossibility of describing the universe as a whole, and starting from the whole? I don't understand. That's not the kind of questions I address. I think it's Baptiste that asked that. It's not the kind of question on which I can say anything. But I find it that to describe the world is much more convenient to forget about the description from the whole, because quantum mechanics, the only thing I find useful and coherent, and that can take us ahead toward quantum gravity, is to describe the world from within. I mean, we get confused every time we forgot that we are looking at the world from within. But one of the confusion about quantum mechanics is exactly that it makes sense when we are one system that interact with the other. So the true facts are the true facts with respect to us, and they're super true. They're real. We don't need to get out to infinity and see things from a distance to get coherence. And there is a number of very different directions in which I see piling up evidence that monism is a bad idea. The argument about time that Mauro has been working out, quantum gravity, where you don't have a space-time, cosmology, interpretation of quantum mechanics, they're all independent things, but they seem all to me all to point out in this direction. And so I'm just, you know, essentially listening to Mauro and learning. The last point is about structural realism that Matteo discussed. Let me say one last thing about monism. I loved the mosaic, the Humean mosaic picture. When I read David Lewis, I was completely captured. I think it's completely misleading. It's horrendously misleading. If you want to think about quantum gravity, it just doesn't work at all. And if you want to think even about simple quantum mechanics, is misleading. Now let me get to structural realism. Once again, as Mauro said at the beginning, you can relational quantum mechanics is not a philosophy. It's a perspective on is how to think about quantum mechanics. So obviously it might be compatible, might be readable within different philosophical perspectives, and even if it's very far from some and sort of bring water to others, of course, like any form of knowledge. In fact, at the beginning, I was attracted by structural realism, less so. One of the reasons is just I got completely unconvinced of the original argument that structure are more historical stable than objects. I talked history of physics. I mean, the sun is always the sun through all the changes, and water is always water, while structure has been changing much more. But more to the point about ontic structural realism, I see the appeal of it, and I also see the limitations that were nicely presented by Matteo. And regarding relational quantum mechanics, Matteo is right. We talk about systems, and of course one can say if a system has properties which are not intrinsic to the system, but are relational, I'll come in a moment to Hanno questions about what exactly are these problems, where we knew that before. Then, of course, relations count much more than before, so to say. We don't think the world as a collection of entities, each one of these properties, but we need the relations, in fact, and in particular the interactions, to make sense of the property of the system. Now, of course, one can try to push that and say, as Lara has written, but then the systems are not much more than nodes between the properties. What we're actually describing is the quantum events. And sort of the harmonic oscillator is a connection between quantum events. Schrödinger went quite to that direction at the end of his life. From the realistic integration wave function, he went all the way to write a particle is an instantaneous, is a collection of instantaneous events separated. But in physics, we use the notion of system very much. We organize the events using the notion of system dramatically. So it's definitely part of that. And what is really happening is that a system, all the contingent property of a system, so those that change in time, if you want, these are the ones we're talking about. Not the mass of a particle, which does not change in time. Pierre had this nice separation of three kinds of properties. The first kind, which we say a system is characterized by some numbers, something. These are the properties of the system as such. But then there are all the variables, the contingent property, which are those that we describe, let's be precise, as a function of phase space. Those which are collected by the phase space, so to say. So everything which is a function in phase space, which change when in the dynamics, these are the quantities we're talking about. And these are the quantity to which we associate operators. So these are the quantities that we measure. These are the quantities relational quantum mechanics interpret as not pertaining to the system itself, but pertaining to the interaction between the system and something else. So this is what we're talking about specifically. But then, of course, what is a system without properties, right? So it becomes a very weak notion of system. What is a particle which doesn't have a velocity, an angular momentum, an energy, doesn't have any of that? Well, it is a system, fine, but its existence depends strictly by the properties that depend on the other things. So the point is that the systems, in some sense, have no independent existence. And this is very close to metaphysical coherentism, the way I read it in my naive physicist view. And those who have read the book have written recently, Helgoland, know that I must heal from that, probably because I heal from my falling in love with philosophers. But I should come out from my Nagarjuna fascination, which is all about, if I say metaphysical coherentism, namely the main thesis is that systems have no independent existence. Nagarjuna is not saying that there are no systems. He's not saying that there are no objects. He's saying that an object doesn't have an existence and properties independent of anything else. So he said that anything can be only understood in terms of something else. And of course, the point is that they all explain one another. So it's, he called it sunyata, vacuum, vacuita, emptiness. Sorry, I forgot the English name. Because emptiness. He says things are empty. Doesn't mean that they don't exist. It means don't exist independently. They have no properties independently of anything else. So is this interdependence, which it seems to me quantum mechanics has brought out, which I would call contextualism if Alexia hadn't sort of stolen the Bohr word of contextualism for saying something more specific. So it's the mutual ontological dependence, which, in my opinion, Nagarjuna so nicely argue for, which seems to be, centuries later, beautifully revealed by quantum mechanics. And to the question, are relations prior metaphysically? I am not a philosopher. I don't know what prior mean. I know what it means to use a set of notions in my conceptual structures more fundamental than other. But I guess I'm less a metaphysician that many of you. But my instinct after my fascination with structural realism is that the way I put it in my book is that I think if Nagarjuna was alive now and had a new edition of his books. You know, his books is always little chapter, and it says, you know, objects are empty, space is empty, time is empty, the self is empty. I mean, meaning none of these things have independence by itself. I think he would add a one chapter saying structures are empty, namely structure by themselves are not sufficient to make sense of all the rest. They are part of a story. Like in fact, he has a chapter in which says emptiness is empty, meaning exactly the same point. Now I close. I've talked too much. Just I've added here because Hanno made the question: what are the quantities that are relational and didn't we know before? The quantities which are relational are the variables on phase space for each given system. Didn't we know before? No, we didn't. Many of those we did. I mean, because there are a lot of relationality in physics. But you know, even in general relativity, if you have two particles a distance of a meter, they're a distance of a meter. In quantum mechanics, they're a distance of a meter with respect to somebody else. In fact, there are some experiments in which the proper time of the same particle on the same interval can be in a quantum superposition of two things. So it becomes definitive only at the moment of interactions. So there are many, but of course, as Hanno was saying, given a system, there are always quantity. Given a quantum system in a theory, not the object, given a piece of theory, there are always quantity in the theory which are not relational. Okay, the coupling constant, the mass, and others. Careful, because quantum mechanics, of course, is a collection of is a structure, is a scheme for treating theories. The larger the theory, the more quantities tend to become relational. And the two examples that Hanno made are very much the point. I mean, suppose we have a number of photons and a number of electrons. Who would say that the number of photons is relational? Who would say the number of electrons is relational? Well, answer anybody who studied quantum field theory. I mean, quantum field theory, the number of particles is a number operator n, which generically, the quantum state of the field is a superposition of the two. It may very well be, you can concat a Wigner-French situation in which the number of particles, in fact, quantum properties of black hole describe exactly this. There's one observer with respect to a certain number of particles, the other observer with respect to a different number of particles, because it's making a measurement in a different basis, so to say, or simply because it's for one the number of particles define it, the other not, because there is a correlation with observer. So the relationality quantum mechanics talk about is very precise. Is the variable on the phase space, classical system, or the operator algebra, quantity described by the operator algebra, given a theory. Given reality, it's much more complicated because it's theory dependent. And definitely, if you fold in quantum field theory generativity, the amount of relationality in a larger sense is huge. Because generativity, there is localization, which is relational, in addition to all the quantum one and all that. Okay, I've talked too long. This is a set of reactions. Hope they were useful. Again, thank you, and I'm curious to all your questions and looking forward to all them.
Thank you, Carlo.
And comments.
Okay, so I would, if my colleagues, fellow organizers agree, I would do a first round of replies or counter comments from the speakers. I mean, if you have any, or you can wait. So if you guys want, just put a Q in the chat and I'll give you priorities. While we're waiting, I think I can start. Oh, sorry, I forgot. We have questions from the last talks too. So there was a question from Matteo for the second talk, I think from Pierre.
Okay, yeah. Okay, let me remind it. Okay, yes, I have it. It was a really small remark on something that Carlo also mentioned. I was really a bit puzzled by this distinction between intrinsic, contingent, and relational. now it has become clearer, but it sounds really unconventional to me from the philosophical perspective, because usually what I was used to is this distinction between intrinsic and relational, and really this contingent, essential or necessary distinction is regarded as orthogonal in a sense. I mean, intrinsic properties might be contingent or not. I understand that you're using intrinsic in the terms of non-contingent, but be careful because, for example, I don't know, you might have examples in which the property is intrinsic in a sense, but not in other sense. Mass, for example, it is intrinsic. I'm not sure because it is non-contingent in a way, but it is connected to the presence of an Higgs field, so it is relational. I mean, I was a bit worried about confusion about different philosophical categories, but nothing really important.
Yeah, no, you're right. I guess you're right. Period.
Yeah,
I just wanted to specify that contingent in the sense in which the variables relational quantum mechanics turn out to be relational. Which ones? The ones which are contingent in the sense that they're the ones that vary when the system evolves in its phase space.
Yeah, I got it clear, but I think it's safer to use state dependent and state independent. And
okay.
Both properties might be intrinsic or not. I mean, that's a different question.
Yeah.
And it's an even different question whether they are contingent or necessary in the traditional philosophical sense.
I got it.
By the just,
I got it.
Yes, I also agree. I mean, the denomination was not standard at all, but so far I just wanted to get one word to describe each property, like one adjective. And for the first, intrinsic, I think it's fine, but then the two others, contingent and relational, they are both extrinsic. But somehow the categories of philosophers, intrinsic and extrinsic, they don't really fit to what I wanted to describe, because I want 3 categories, not 2. So I can pile up adjectives, but then it also makes it more obscure. So yeah,
makes sense to me. But what about mass? I mean, mass is intrinsic in your sense, but it's not intrinsic in the traditional sense. So you should make this clear.
No, I think it depends the theoretical framework in which you are. Yeah. Like in some theoretical framework, mass is intrinsic. Like if you consider that the mass is just a label for the irreducible representations of the Poincaré group, then your particle is described by a Hilbert space, and you have the mass is just a Casimir, and in this case it's fully intrinsic. Then if you are in another theory, like probably special relativity, then the mass, well, this is debatable, but well, you were mentioning the X, for instance. If in quantum field theory with an X particle, then probably it's not correct to say that the mass is intrinsic. In this case, it would be extrinsic. Yeah. But ultimately, I mean, I am convinced that all these properties, they are all relational. Like, I am convinced also that the very definition of system themselves is also relational. It's just that it is convenient for describing some kind of experiments. It is convenient to make a distinction and to assume that some of the properties will not change during the time of my experiment. But for instance, if I want to measure an electron, if I just want to measure the spin of the electron through a Stern-Gerlach, then it's perfectly fine to say that the charge is an intrinsic property during the time of my experiment. But afterwards, I don't know what happened to the electron, but the electron could decay in 2 photons, or all the possibilities that are offered by particle physics, and in which case the physical, what I used to call my physical system, is different, it changes. And so depending on the experiment that I want to calibrate, I have different notions of system.
Thanks.
Okay, so from the previous list, again, I have Richard, Augustin, which, okay, so Augustin is fine, just accept me. Richard, I don't know if you still want to ask the question that you had from the earlier talk for Pierre.
Yeah, sure. I mean, it's a bit general, I guess. It comes down to his point about, well, so obviously a lot of people here are talking about RQM or have a version that's against RQM, or they have a sort of a dog in the fight, if you like. Well, from my perspective, I don't particularly care which comes out as a winner, but it's interesting to know them all for the reasons that have been brought up. However, for me, RQM, I hear about it, I read a paper or two, and I say, oh, that's nice, I'll put it in my drawer of theories that might be true, but I don't particularly pay too much attention. Except for the fact for RQM, there's the additional distinction that a lot of people involved in it are also related to sort of quantum gravity work, which relates to gravity, which is a slightly broader or different area of physics from where this is usually paid attention to. So it's almost an anthropological point for me. I look at this theory and think, okay, well, maybe there's a reason these people who have a background in gravity are also interested. And then it has a different perspective to me. It's not just another model for representing quantum mechanics. It's now, okay, well, perhaps this is more explanatory somehow. And I was wondering, based on your talk, there was a talk about how you got to the position you did. You were thinking from a sort of gravitational perspective at one point, even if it was just in passing reference. I'd be interested to know, from a gravity perspective, why this appeals to you. Because this is, to be really blunt, the sole reason why this is, at a glance at least, any different from any of the other particular theories that are, from week to week, I change which one is my favorite. So I'd just be interested to see your thoughts on that.
Who you're asking to, Pierre or me?
Both, if that's a possibility.
Pierre, go ahead.
Okay. Yeah. I think one reason it is very attractive from a gravitational point of view is because in gravity we are used to this notion of relativization of quantities. Like this is a whole story that starts with velocity. Like with Aristotelian physics, we used to think that velocity was somehow absolute in some sense, which is not obvious, by the way, but still. And then Galilean principle of relativity comes to shake this idea. And then with general relativity, we are going further in this direction of relativization. And so somehow, throughout the history of science, many notions that we used to consider as being absolute have been relativized. So relational quantum mechanics fits well in this picture. Yeah.
Maybe to ask a question that's maybe more hostile than I in fact am. But when you talk about velocity being relational, okay, well I could say, well, you have position momentum is uncertain in quantum mechanics, so that's not so different. Are there, and maybe this is pushing in a technical direction perhaps that should be avoided, are there specific technical reasons why from a quantum gravity perspective this is appealing to you? Beyond just saying, okay, well, in physics there's lots of relativization of things, because that's true of quantum mechanics. You could go from a quantum mechanic argument and say, there's lots of relativity here, so we thought, why not relativize some other things? Which presumably is a big motivation for a lot of the other theories too. Is there specific to the quantum gravity perspective something that drags you in this direction?
Well,
Let me try to answer this. If you just very rapidly but more technically, if you think quantum mechanically from the perspective of relational quantum mechanics, the basic equation of quantum mechanics are the same as classical mechanics, equal, plus the non-commutativity of the variables. Just plus PQ minus QP equal IH bar. That's it. All the rest follows. And what you're supposed to compute is two things: the spectra that comes from the non-commutativity of the algebra, which give you what values the variable can take, and the transition amplitudes. So the thing is about transition amplitudes, nothing else. There's no state that evolves. There's nothing like that. The transition amplitude between what and what, because transition amplitude between here and here, but what is here, what is there? Well, between interaction with something and interaction with something else. Now this fits wonderfully with the way I think about quantum gravity. because the way I think about quantum gravity, it's exactly that. I mean, I'm in a classical regime. There's a quantum gravity phenomenon. I want to know the transition amplitude between the beginning and the end. And I don't want to know what happened in between, if there's a Schrödinger wave evolving or anything like that. So I've just transition amplitudes. In fact, one way of defining loop quantum gravity, which is the way I'm using now, is just in terms of transition amplitudes between states. So the states represent the boundary of the region where something happened. And the beauty here is that what is a system in relational quantum mechanics is just a portion of space-time in quantum gravity. So the relationality of GR, it's really the same thing as the relationality in quantum mechanics. The Heisenberg cat is the boundary of the region. So everything sort of fits nicely, which of course, it's a good selling point only if you like loop quantum gravity. But for me, it's a way I can think how to compute what happened at the end of the black hole evaporation, for instance, without having to go to infinity or to do things like that. Your question was general, right? It wasn't specific, so that I gave you this general.
I just wanted to maybe clarify it, if only in my own mind. So listening to you guys talk, I was thinking when you're talking about a relational perspective on these things, if you were to take a spin foam and then say, okay, well, a local observer, if you like, is somebody who has a position within the spin foam and is looking at it. And that is your initial state, and then your transition amplitude is where you're looking to end up, or where you were anticipating ending up. Is this related to this?
No. Daniela Ritt is here also. No, look, the spin foam is a Feynman integral. Feynman integral is always Feynman integral between some initial to some final. You're summing over the path from here to there. So you'll Feynman integral compute transition amplitudes. I know that in quantum field theory you want to put insertions inside, but I don't think this is so useful in quantum gravity. People are trying also. I'm not saying it's wrong. But I think that the transition amplitudes are far nicer. We're going to technicalities which are not on the, and again, the question is not, is that the only logical possibility? The question is the one in which I think I might be able to compute something.
Okay, thank you.
Okay, there was another question on Pierre's talk, which I forgot about, and I apologize, from Mauro, and you can ask it now if you want. Dorato.
My audio is off.
Now it's on.
Okay, now it's on. You seem to equate mechanical theories with locality. But mechanical theory is just simply about particles and forces. And so I wouldn't do that identification, but this is just a simple suggestion on my part. And the problem seems to be that it seems you're forgetting the fact that you can derive the Bell inequalities from just two premises, namely quantum correlations on the one hand, and now I forgot about the second premise. But, but it's
some sort of no.
Well, and the
information transfer.
Locality,
yeah.
Quantum correlations and Bell locality, and these two imply they imply the Bell inequalities. So obviously, if you want to reproduce the quantum correlations, then you have to give up locality. So you don't start from a realistic assumption. So really these are realistic assumptions, so to speak, is the end point. So reproducing quantum correlation and the Bell version locality, that gives you Bell's inequality, and of course, since that it violated, then you have to abandon locality. So I'm wondering whether locality just goes across all different interpretations, unless you go for the many world, of course. And maybe Carlo wants to add something to this. I think Federico Laudisa has insisted many times on this, so that if you want to reproduce the quantum correlations, and if you start with the Bell definition,
yes, this is really Pierre's point. This is true, and the derivation of the Bell inequalities from two things that you're referring to, of course, is correct. But one of the two things is the one you call the Bell locality, and that Pierre called the local causality, which is a very specific mathematical formula, which refers to the assumption that there are no relational localized beable. That is an assumption that Bell held dear to his heart, and so was part of his framework. And what Pierre is suggesting, that if you drop that assumption, you might say, okay, so you've given up locality in some sense, which is true.
Okay.
But the analogous of the Bell local causality with more general beables, which are relational quantities, does not lead to a violation of the Bell inequality as is
usually
within the laboratory. Yeah,
I agree. Yes, I agree. Sorry for the second preface. It's like forgetting the joke, the pun of the line of the joke.
Okay, so I'm gonna move on. So let me clarify. I get all your questions. I'm just going back to the previous ones. So now I think just to have some kind of order in the discussion, I suggest Anok and then Philippe ask questions which were about Alexia's talk. And then after Philippe, I think there's going to be a follow-up from Richard Ely. So this is the order for now. And I'm sorry to leave Danielle and Luca for waiting, but there is time for everyone. So Hanok, you can go next.
Thanks very much. But my points were already raised, so not to pursue it. But if Alexa can put in the chat, sorry, a link to her to the talk she mentioned, I'd appreciate that, which she is about to give soon. Thanks.
Yeah, it's the new direction in Foundation. Alexia, if you have the link, please share it. Otherwise...
Yes, I do that right away.
Cool, thank you. Okay, Philippe.
Yes, yes, so I had some comments about Alexia's, etc. But I have a question to Carlo from what he just said about the Feynman diagram in general relativity. You calculate transition amplitude basically between initial and final state, but your states, are they stable facts? Can you say this initial? For me, when you do a Feynman calculation, it's exactly that. You go from a stable fact to another stable fact. So would these states with codes be stable facts? Did I understand it correctly? Oh.
In a realistic use of the probabilities, yeah, we're interested in stable fact ultimately, because those are the ones. We live in a semi-classical world, so this yes. Connects to your framework, right? I mean, at the end of the day, we always want to bring back the connection to the macroscopic classical yes. world. So in a sense, we go toward you, or even toward Bohr, in a sense, right?
It could even be a modality according to our terminology. But yes. Yes, so this is the essential point. Yes, I think you explained it quite well between CSM and you have these stable facts which are obtained in some approximation by using decoherence, whereas what we say is that this limiting facts that we call that is the context, the fact that there is a system and a context, this defines what we call a modality, and actually we need the modality for the whole construction. So for you, you sort of skip them and then get them to some approximation at the end, whereas in our case, we put it right at the beginning because we claim that without that, we go nowhere. And especially you invoke decoherence. but decoherence is not that clear. It's not absolutely clear that you can, in some sense, reconstruct the classical world by using decoherence and classical mechanics. I had many discussions with Jurek about that. I still don't agree with him. He starts from let be psi, he does something, and now he's even himself, that is Wojciech Jurek, the father of decoherence, he feels compelled to add, this Darwinism and all kind of stuff, which becomes a little bit mysterious, to finally maybe get the classical world from quantum plus decoherence. So what we say is that simply it does not work. Let's agree that it does not work, and then you need to have this bipartite sort of reality. Which is the context and the system. So it's, in our case, it's not approximation. It's not an approximation. Stable facts are not an approximation. They are a requirement to do any sense from the full stuff. So you see, it's a rather deep difference. Technically, it's not. We have many agreements, many common points, but in some sense, we take the thing opposite way. We need the context at the beginning. Otherwise, after 40 years of thinking about that, I think we are stuck. We cannot end up in something really stable. But it fits with you. I'm very happy to hear that it fits in the way you do your calculations, because our modalities are asymptotic states, actually. I can explain that in more details if you want. So if you say what I need is asymptotic state to do Feynman diagram calculation, it perfectly fits with me. I'm really happy about that. And then we will agree. I think in some, yes, but you see, there is a little bit of a philosophical difference in the fact of getting the stable facts as an approximation at the end of the process, using decoherence, which is, or starting from the fact that we need them, otherwise we go nowhere. We cannot even construct quantum mechanics. We reconstruct quantum mechanics, but we start from systems and contexts. It's a little bit Bohr-inspired, you remember? Well, so I think we are very close, I think, but there is still this difference about ontology. In our view, contexts are part of the ontology, which is a little bit bizarre, but well, quantum mechanics is bizarre, as my master Anna Aspe like to say. Carlo.
No, we should go to the next question. I mean, I don't want to continue this. We can go to the next question, I think. If
okay.
That enough.
So there was a follow-up actually from Richard. So you can go, Richard.
Thank you. Yeah, follow-up to Philippe. I'm very confused about his notion of a hard context. It sounds to me reminiscent of Bohr and his insistence on a classical description, something imposed from the outside rather than, in some sense, flowing naturally from quantum theory. So what do you mean by hard context? Where does it come from?
It's exactly what you say, Richard. Well, Bohr, it was a long time ago, and Bohr said many things a little bit contradicting each other. But yes, it's the same idea as Bohr, that we do need a sort of a classical reference. Now, the question that everybody asks is that if you do that, you have this Heisenberg cut between the system and the macroscopic context. And then how can you then you use quantum universality, it seems. But I think it is not true. People have discovered many years ago what is called algebraic quantum mechanics. And if you extend classes that is so-called type 1, if you know this language, usual quantum mechanics to type 3, then you have automatically this, the fact that you have super selection rules everywhere, that the center of algebras are not you don't have only type 1 algebras. So there are all kinds of properties which can be inserted in the math from the start using algebraic approach. And because it's sort of managing infinities in some sense. You see, if you take an infinite number of particles, von Neumann already showed that, you blow up the Hilbert space structure. You don't have a Hilbert space anymore. It becomes completely unmanageable. But there are ways to get out of that. And then you can put in a unified mathematical structure both the standard quantum mechanics, type 1, and the way to manage macroscopicity, let's say. And this is mathematically possible. This is just really complicated, and also the dynamics. If you want to calculate any dynamics in that, it's a mess. But still, the mathematics are not nonsense. They are feasible. They are not very popular nowadays. Everybody invokes decoherence, but I must say I'm not really happy with that. And the fact that the fact of managing a bipartite ontology is not incompatible with mathematics. It can be done, just tricky. Do you agree with that, Richard? It seems you agree.
Thank you.
Okay, thanks. So actually, we don't have too much time and we still have 3 questions. So I have Lev next.
Thank you for talks. And Carlo, I really want to understand relational quantum mechanics. I had your talk about a couple of months ago and now, and mostly what I get, what's wrong with the wave function? And then in questions, I want kind of basic ingredients. And you say you have systems, which is not exactly clear for me. They should be macroscopic, or photon is a system, or not. But then later you really said about what is your, and you mentioned things which are completely out of my vocabulary in quantum mechanics. You said events. I have no idea what's event in quantum mechanics. You said phase space. I have no idea what's phase space in quantum mechanics. You said transition amplitude. It's a technical term which I think has none. It is just, you know, some expression that I cannot understand any fundamental meaning for this. And then you said that really what you want to do is you consider classical mechanics, and then it's not commute, and then you will do something with it. I know classical mechanics is wrong. I forgot about it. So if, may I understand that you want to do quantum gravity, which I didn't try, and you see that quantum mechanics doesn't work. So you want to find a new framework, maybe coming back to classical mechanics or something like this, in which you believe that quantum gravity will work. Or you do try to find the interpretation of quantum mechanics with this measurement problem and this kind of thing. Because I don't see an advantage of this relational thing. I always can consider system A and B, and then I will answer any question, A relative to B, when I consider all of them, both of them together.
Carlo.
Sorry.
Yeah.
Thank you, Lev. If you're genuinely interested in understanding relational quantum mechanics, just read Helgoland. It reads easily and fast. Its last book is entirely about that, and it has all the ideas. Or read a couple of papers on mine. The last ones are. In fact, my last paper on the topic, which is an answer to some questions by some people about relational quantum mechanics, is a very synthetic version of it. But let me answer the specific question that you phrased, because some of them are very interesting in my opinion. One is, what is a system? I think that the good way of thinking about quantum mechanics is not our understanding of the elementary constituencies of reality. That's something else. It's something else. For instance, if I have a molecule, the molecule rotates and has angular momentum, I can study the angular momentum of the molecules using quantum mechanics. And this is completely irrelevant of the fact that the molecule is made by atoms, and the atoms have nuclei and made by quarks. What is relevant is that in interacting with the molecule, I have a certain number of variables that describe the way I interact with the molecules, a finite number of variables which are sufficient to describe its interaction in the approximation in which I'm working, which I'm not breaking it apart. And these variables are a set of variables, which in the classical limit are functional phase space. But if you don't want to think about the classical limit, just think about quantum mechanically. So they're described as a set of variables. In fact, technically it's an algebra. And as an algebra, they immediately have a spectrum, because you can associate a spectrum to element of an algebra. And immediately this gives me the first prediction of quantum mechanics, which is that, for instance, the value of the angular momentum are quantized. And if I measure, bingo, they're exactly quantized. This has nothing to do with the component, the constituencies, what is made. This has to do with the fact that a system which interact with me through a certain number of variables, these variables have a quantized value. Not only, if I measure, let me use the standard Copenhagen language. If I measure some variables, which is what, Alexa would do in her lab all the time, and then I measure again, as you know very well, I can compute a probability distribution of what is going to happen. And to do that, I have to compute some transition amplitudes. So transition amplitude spectra exhaust all the predictions. Out of those, I can compute everything about the world. To do that, I have to say, what are the systems? What are the variables? There's the algebra, and of course, what is the Hamiltonian if I'm evolving in time. This is the way I find it more useful to think about quantum mechanics. And quite remarkably, if I may, as I've written various times, this is the way quantum mechanics was born in 1925 in the work of Max Born and his collaborator Heisenberg and Jordan and Dirac. And I am well aware that, of course, 1 year later, Schrödinger wrote the Schrödinger equation and everybody got in love with this evolving wave. But I find it that at 100 years later, at the light of the infinite confusion, the Schrödinger evolving thing, the evolving state, this wave, leads to a coherent picture, which I find less useful for doing quantum gravity and less useful for understanding quantum mechanics. So system is something which is clearly defined. If you don't like phase space, just take the algebra observables, but it's nice to know that all classical system, quantum system, a classical limit, so we can see what are the variables in the limit. And this is the function of the phase space, and all the information are in the transition amplitudes. And please, we have different ways of thinking about quantum mechanics. What is interesting, I think, is that there are different ways. And not just, we're talking about relational quantum mechanics. It's fine that everybody says, oh, I have a better way, and it's this and this and this and that, and explain what it is. But all right, we know that there are alternative ways. And I'm not saying that they're incoherent. They're not incoherent. That's the point I made, the first thing I said. The interesting fact, there are different ways of thinking about quantum mechanics. Each seems incoherent to those of us who are focused on seeing quantum mechanics from one perspective. The beauty of nature, as Feynman said, is precisely the fact that it can be interpreted in different manners, in the different ways. And in quantum mechanics, we are so in disagreement of what is the best manner to think about it. People are ready to swear on their mother health that the Brody bomb is the right way, or Manywold is the right way, or Everett is the right way. There are different ways, and I think a careful discussion, listening to one another, may help us to make some progress, because we are going ahead in this discussion. We are not in the same point of 15 years ago.
Just maybe.
I'm so sorry, Lev. I'm super sorry. We have 2 questions and we are late, super late. So, and I also have to apologize with Ding and with Anok for not being able to take your follow-ups. I'm gonna stick to the list and ask to Daniele and Luca to keep it quick as possible, at least. Daniele, you're up next.
Yep, I'll try to be quick. So only 2 very brief remarks and then a slightly longer one. Actually, I'll skip the 2 remarks. I don't care. I'll just tell you the slightly more substantial comment. I would be interested in hearing Carlos and the others' opinion. So I'm intrigued by the question how epistemic is relational quantum mechanics. And I think we all agreed that in the terminology of the epistemic ontic divide of the Harrigan-Speckens formulation, we are on the epistemic side. That's fine. The issue seems to me, on the one hand, what are the systems that count as observers? And related to that, what is the interpretation of probabilities we attach to quantum mechanics? And in other words, if the observers are anything like a relational quantum mechanics and not agents, or equivalently, everything can count as an agent, and correspondingly probabilities are just objective chances like propensities, context-dependent objective chances, then there's no epistemic element at all, really. It's we have in fact, we also mathematically we know the quantum states are just a list of probabilities, so if probabilities are objective chances, then we have contextuality, we have relationalism, we have some form of perspectivalism. But quantum states are just part of the relational, contextual, ontological structure of the world. They have nothing to do with epistemology. At least that's my understanding of the situation. I don't know if I'm misunderstanding something, or if anybody has some refinement of the view.
I have my answer. I agree, 100%. I think it's very correct. What is and it's acute. The confusion about the word epistemic is strong, and you're clearing it out entirely. How to think about probabilities brings in the discussion about probability, frequentist, Bayesian, but it's not the same thing. I mean, I think they're two separate things. I mean, just if you want to think independently of any knowledge, you may think that the same spin up in the z direction. A million of time interacting with a spin x apparatus, half of the time goes one way, half the time goes what way, and that's what we mean by probability. So it's a statement about repeating things in the world. So if you want to call this objective probability or frequentist interpretation of probability, or what you're ready to bet about what is going to happen next, it's a different question. But there's nothing epistemic by itself in the theory.
I think that's the relevant question, because quantum states are just this list of probabilities. So if we decide that probabilities can be attributed to individual events and not just to sets of identical events, so we don't apply a frequentist interpretation, then the choice is between some objective chance disposition type, dispositionalist type interpretation, or subjective Bayesian with varying degrees of objective elements and evidence-based judgments. But that's real the difference about quantum states.
I know that debate, but that's a debate of the interpretation of probability, and I think we shouldn't confuse the very interesting debate of the interpretation of probability with interpretation of quantum mechanics. It's a fact that when spin z up particle go through Stern-Gerlach apparatus, half the time go that way, half the time go that way. And as far as we see, there isn't any rule except randomness that we ever have been able to figure out in the world. So whether you want to conceptualize this in terms of ignorance or in terms of dispositional properties that Mauro has been talking about, or in terms of even Lewis, non-deterministic mosaic, out of which you read frequent probabilities of frequencies. That's another story. That's a story about philosophy of probability. From the point of physics, these, in my opinion, they're all equivalent.
Okay, so Luca, very last question.
So thanks. I don't know if I survived the connection. I have really bad connection. So first I want to thank everyone that participated. And please let me know if you don't understand me, because the picture is freezing now. I don't see.
No, it's very clear. We're hearing you very well without any problem.
Thank you. Thank you. So I have a question about or a comment about the role of the rest of the universe or the environment and the objectivity of the relative quantities. So I agree that only relative quantities or relative information between two objects or two systems is knowable and is in a way is objective. And the problem with relational quantum mechanics is a little bit this Winger's friend type of scenario where different observer or different system have different contradicting information. So I have no problem with stable facts if you, but this notion of relative facts is a bit strange, and I wanted to ask. So I have a bit boorish proposal or solution to this problem, is because relative quantities or relative information is only objective or given or measurable or whatever, definable. Relative quantities are only definable if the rest of the universe or the environment is separated. So within a system of two objects, object and measurement, the relative quantities are only definable if this system is separable from the universe and from the rest. So if Wigner wants to measure a contradicting observable that's not compatible, he will disturb my system in an incredible way that I cannot define any relative quantities. This is also true in a classical context in a way. So I cannot define distances if someone is pushing me around constantly. So, or my labor is shaking or whatever. So I wonder what you say about this proposal and about the role of the rest of the universe, or that if separability that's a condition for you to have knowledge or objective facts. Thanks.
Yeah, I wouldn't disagree with many of the things you say. Only we should, first of all, specifically quantum systems, we know very well that specific to measure quantum properties, we have to isolate systems, right? Otherwise, decoherence cancels interference. It's very hard to. That's why it's hard to do quantum computers. But on the other hand, we also use quantum mechanics, to understand why the sun works, why the sky is blue, and how galaxies formed in a situation which was a great mess and everything interacting with this. So what you said is correct, but it should be made compatible as a physicist, including approximations and this and this and that, with the actual use that we do with quantum mechanics in situations in which nothing is isolated. I'm not contradicting you, I'm just pointing out that quantum mechanics should work in a far more...
In a way, it's
a very
isolated. Sorry. Okay. For me, a little bit the possibility to separate system or objects from the rest and to describe it as free object is a bit a condition of being able to define the objects themselves.
Yeah.
Otherwise, objects would not realize themselves in a context.
I agree. I think what a quantum system is.
That was a bit my point.
Yeah, I think what a quantum system naturally is a portion of the universe that, to some extent, to the extent in which we are interested in, can be considered isolated for a little while.
Okay. I have to apologize again for being so strict, but we are late, 20 minutes late. And for this, I apologize with Carlo and with the speakers. So let me thank once again, Carlo, especially because he replied to our questions. Now I'm gonna give the stage to Andrea, which is going to thank people.
Yes. So the workshop is coming to the end. So let me thank once again our speakers, Pierre, Alexia, Mauro, Matteo. So they accepted our invitation. We're very happy. I'm very happy for the very stimulating talk and for our discussion. I want to thank again very warmly Carlo Rovelli for having accepted our invitation, for his answer to our question, for his availability to discuss relational quantum mechanics, and of course to everyone that joined us and that participated to the workshop. Really many thanks for your comments, for your question. So I hope that this will be the first step to discuss relational quantum mechanics and the philosophy of physics community even more, to discover this theory, to proceed with the understanding of these, I would say, very interesting and hopefully fruitful perspective. So let me thank again also our institution, Institut NEL, Université of Genève, Université de Lausanne, as well as our funding agency. So also many thanks to Claudio and Christian for having helped me organizing this event. And so many thanks to everyone for having made this beautiful and wonderful event with us. So bye-bye. I don't have anything.
Thank you very much.
To say.
Thank you all of you. For me, it has been extraordinarily interesting and useful. So thank you for